everyone, I'm Rahul Huilgol. Today, Dick and I are going to be talking about mixed precision training with Apache MXNet. We'll take you through the motivation for why use mixed precision training, how to use it, and how does it help. Over the last few years, we have seen deep neural models get larger and more complex. Taking the domain of speech recognition, for example, deep speech architecture from 2014 had about 10 million parameters, whereas the deep speech 2 architecture from 2016 had about 110 million parameters. Datasets are also becoming larger than ever, increasing the time for training. These trends translate to increased resource requirements, both in terms of compute and memory. Traditionally, deep learning computation has used a single precision float with 32 bits. Using reduced precision for representation and computation offers an opportunity to address some of these requirements. Using half precision floating point with 16 bits instead of single precision doesn't just help with reducing the amount of memory used by the model and the pressure on the memory bandwidth. On hardware with specialized support for float 16 compute, the time for arithmetic can also be reduced. Using half precision float in combination with single precision float is referred to as mixed precision. We'll see later how that combination exactly works. I mentioned the hardware support for float 16 just now. But the earlier support for float 16 was only as a storage type to help address memory requirements. Compute was often slow because it involved casting to float 32 and back. Recent GPUs, like the Volta range of GPUs by NVIDIA, have what are called tensor cores, using which float 16 compute is theoretically 2 to 8x faster than float 32. Using mixed precision for deep learning thus provides an opportunity to speed up training and inference on such hardware, along with the advantages in terms of memory. But maintaining the same model accuracy as float 32 requires us to make some special considerations due to the inherent reduced precision of float 16. Let us go through the three key challenges with using mixed precision and discuss how to overcome them. At each step, I'll introduce the API for using mixed precision or that feature with MXNet, which will give you an idea of the changes needed when moving from single precision to mixed precision. First is the core aspect of maintaining the precision of arithmetic. Tensor cores do not just compute with all float 16 tensors. They have support for accumulating half precision products into a single precision output as well. As this figure shows, we can take the product of two float 16 inputs as a float 32 product and sum it up with a float 32 accumulator. By casting this float 32 value into float 16, we can get better precision for this arithmetic. At this point, the name mixed precision should hopefully be clear to you all. So apart from that, we would want to avoid large reductions in float 16. So this means that layers like softmax and batch norm are preferably left alone in float 32. Let's look at the API. This is how you would generally switch to using mixed precision with MXNet. If you're using the symbolic interface, you add a cast layer to the network for before the layers which need to be computed in float 16. This generally means you add a cast layer at the beginning of the network, so all subsequent layers do float 16 arithmetic. Since we want to avoid doing softmax with float 16, we convert the output of the previous layers to float 32 and then pass it to softmax with another cast layer. Batch norm layers uh, in MXNet take in float 16 inputs but maintain the weights for that layer in float 32, so the user does not have to worry about the computation of batch norm with float 16. With the Gluon API, it's even simpler. We need to cast the block representing the network to float 16 uh, and then again cast the data with another cast. Uh, since softmax is not part of the network, we don't have to worry about casting that here. Um, we would not want to cast softmax to float 16 anyway. Second challenge is that the issue of imprecise weight updates. When we compute in float 16, our gradients are in float 16. If we represent the weights in float 16 as well, then we may run into a couple of issues. Since the range of FP16 is smaller than 30 to FP32, even if the gradient is representable by that range, the update, which is generally the gradient times the learning rate, and often even smaller than the gradient, may not be representable. The update may then become zero. Also, if the ratio of weight update to the weight is large, the update operation for weights in float 16 may not be precise enough and may lead to the update becoming being made zero. To get around this, it is recommended to maintain a master copy of the weights in float 32. In this case, the gradient is in float 16. So the gradient is in float 16, but the weight update is in float 32, and so that the weights can be updated in that. This is activated by using an MXNet optimizer with the multi-precision mode by passing in this field when you're creating an optimizer. For most networks, it has been shown that these changes would be enough to reach the same accuracy as for float 32. But for some networks, they have really small gradients which are outside, most of which are outside the range of outside the range representable by float 16 and may become zero. So we need to deal with this issue of gradient underflow causing the networks to diverge. As an example, here is an histogram of gradients for the multi-box SSD network. We see that most of the gradients are in the left half, which is not representable. We can also see that small gradients mean negative exponents. So most of the range representable by float 16 is lying unused. So how do we solve this issue? Is by loss scaling. We want to shift the gradients to a representable range. So we can scale the loss computed after the forward pass just before back propagation by multiplying it with a certain factor. So all the gradients are also scaled by the same factor and don't become zero. We then unscale the gradients before weight update right after the backward pass. This ensures that weight decay, gradient clipping, and such operations behave similar as for float 32, and we wouldn't need to change any hyperparameters for training. How do you choose this scaling factor? We usually pick a constant factor like 32, 64, 128, and so on, either empirically or by monitoring the gradients and ensuring that multiplying this factor does not cause the gradients to overflow. So this is how the API for loss scaling would look like. With Gluon, you pass in a weight for the loss function. For symbolic, we pass in a grad scale parameter to the softmax layer. For both APIs, then the optimizer is passed a rescale grad parameter so that to divide the gradients by the same factor before updating the weights. I'll now let Dick take you through some results and NVIDIA's experience with mixed precision.
Just to present some of NVIDIA's experience. So I'm talking to some slides that I stole from the GTC proceedings. That's the NVIDIA conference that happened last month down in San Jose. And this slide from the NVIDIA research group. They've basically proclaiming in this case that they've successfully adapted many different types of networks from a purely FP32 form to a mixed precision form and achieved essentially the desired and equivalent accuracy that the larger, slower to train model got. So you can see the whole list of different model types. I'm drilling down on the right side of this slide just in the ImageNet CNNs, but you can see quite a few ones they examined, and for the most part within an epsilon, it's basically exactly the same training accuracy. In the same time, we're also very pleased at the performance increase that you get if you adopt a mixed precision approach. This was really something that NVIDIA doubled down on with the Volta architecture by including this tensor core hardware that's really an accelerator designed for mixed precision. So in this slide, there's really two stories to tell. That one is we're showing the linear scaling behavior from 1 to 2 to 4 to 8 GPUs. Maybe not the best way to see it, but there is pretty much linear scaling. But the other message of the slide is that if you started, say, a year ago on an FP32 ResNet 50 model, you would have the performance shown on the left. And if you stuck with that now in 2018, year-to-year improvement is, incremental, I guess, at best. However, if you instead embrace this mixed precision model, you can see there's quite a sizable improvement. In fact, oops, sorry, wrong way. For ResNet, it's in excess of 3, and you can see for some of these other RNN style models, it can be even greater. So just concluding for both Rahul and myself, mixed precision training, we're bullish about it. It has many benefits. The first of all being it's faster to train, and the model itself is smaller, and then you can use that benefit in various ways, trying more models, deeper models, bigger inputs, etc. I'll jump down to the bottom to say that also, as I said before, the training accuracy is right in line with what you'd get on a fully FP32 model. And then, as Rahul talked about, there are certain considerations, things you have to think about as you take an FP32 model and make it a mixed precision model. At NVIDIA, we've studied each of these potential issues, and we've come up with these workarounds that are listed in the slide. If anyone's interested in learning more about mixed precision training, there were a couple of talks at GTC. I think at this moment, those are available for the attendees for replay, but soon it'll be publicly available. So there's over 2 hours of a much deeper treatment of this, also on NVIDIA's web, various blogs and user guides. And thank you.